The first few chapters of Calc here have dealt with differential calculus. In other words, we're taking the derivative, which you guys should remember is really looking at the slope of a tangent line at a certain point. And we've looked at some of the applications of derivatives. Well, pretty much in math, if you can do something one way, there's always the reverse operation. We're now going to start moving into integral calculus, which happens to be the reverse operation of taking the derivative. But it also happens to be related to finding the area underneath of a curve. In the first 2 weeks of this course, we looked at finding your slope, your instantaneous rate of change, and we also looked at finding your area. If you take a look at your area from A to B underneath this curve, that's what this symbol means. So looking at the graph at the right, we'd be looking at our area from 2 to 6 of this function here, which at this point you don't know how to work it out, but it ends up being this, and that's your approximate number of units for that blue area. We'll get to a point where you'll be able to figure this out exactly. So just like with taking derivatives, we can do the reverse derivative, which is called antiderivative or anti-differentiation. So if we consider this function here, y is equal to x cubed plus 2, and we do its derivative, we get 3x squared. The next one for g, we do its derivative, we also get 3x squared. When we're looking at h, we also get 3x squared because remember pi is a constant. Or looking at m here, we get 3x squared. So in other words, if we started out with 3x squared and we were working backwards and we were integrating 3x squared, we know that we would get, move your exponent up by 1, and then there's really going to be a plus c, because for all these up here, there was always another number that could have been added at the end. We don't necessarily know what that number is, and so we go plus c for some constant. So in general, if you have a function, small f of x, and you do your antiderivative, which is capital F, you always need to remember to go plus c when it's an indefinite integral. An indefinite integral does not have any bounds here. A definite integral like what we had back here has bounds, and we don't have to go plus c, and we'll explain why in a couple more sections. So here we have a constant. So you got to think the derivative of what would be 3? Well, that would just be a 3x, but then you have to remember plus c because it's an indefinite integral. Here you have a 2x. Remember, you have to increase your exponent by 1. So because you're going backwards, doing the reverse of the power rule, and so we get an x squared, and we'd have to have a plus c because it's an indefinite integral. So here we'd have to have our plus c, increase your exponent by 1, but then you got to think, okay, if I did my derivative, there'd be a 5 that would go in front. I don't have a 5 up here. So you have to think, what would I have to have in front to undo that 5? And well, that would be a 1/5. Down below here, you need to think the derivative of what is cosine. And well, that's just sine. Being an indefinite integral, you need to go plus c. Here, you got to think the derivative of what gives me sine. Well, we know that that's going to be a cosine, but actually it's going to be a negative cosine, but you got to think, do I need to have in front to undo my chain rule? Because if I did the derivative of this green, I would get an extra 5 showing up. So you'd have to have a 1/5 in front. That negative is there because the derivative of cosine is a negative sign, so that negative offsets it to make it positive. So in general, when you integrate, you're going to have your plus c. Your exponent's going to go up by 1. So then you got to think, what do I have to have in front to offset that? Well, that would be 1 over whatever that new exponent is. And this always works except when your exponent is negative 1, because the integral of 1 over x, if you increase your exponent by 1, you would get x to the 0. X to the 0, you should know, is 1, and so it doesn't make sense that your antiderivative would just be 1 for this problem. It ends up, when it's 1 over x dx, ends up being the natural log plus c. And we'll get into that once we get into chapter 5. So here you got to think the derivative of what is cosine. Well, that's sine, but and you have your plus c, and then you got to think, what do I have to do to undo my chain rule? I'd have to have a 1 over k in front, because the derivative of the inside's k, and I'd have to undo that. Here, you'd still have to have your plus c. You'd have to undo your chain rule, so you'd have a 1 over a k, but there's also going to be a negative hanging out, because the derivative of cosine, you know, it's negative sine. And we don't want to have a negative sign, we want a positive, so we got to change this. And then similarly for secant, you got to think the derivative of secant squared, or derivative of what is secant squared, and well, that's tangent. You have a 1 over k because you have to undo your chain rule. Derivative of what is a cosecant squared? Well, you know that that's a cotangent with a plus c. Then you'd have to undo your chain rule, so you'd have to have a 1 over k. There's a negative here to offset the derivative of cotangent, which is negative cosecant, and we did not have a negative cosecant. So then here you got to think the derivative of what is a secant tangent. Well, that's just secant, and then you have to undo your chain rule. Similarly over here, the derivative of what is a cosecant cotangent. Well, that's just a cosecant, undoing your chain rule and undoing your negative here in front. So here we have 1 over x. Remember 1 over x, what we said a couple slides ago, goes through the natural log of x. Indefinite integral, remember, plus c. Here you'd have to increase your exponent by 1, it'd be 2. That means you'd have to have a 1 over 2 in front, but that 1/2 in front with this 2 would just be an x squared. Increase your exponent by 1, so it'd be a 3x, and then your plus c. Over here, you'd have to increase your exponent by 1, so then you'd have to have a 1 over 11 in front to offset that exponent, and then you'd still have to have your plus c. So this is anti-differentiation. Now the power rule, working backwards, that we've been using does not work when your variable's in the bottom. Also, I'm going to rewrite my root as a fractional exponent. So now I'm going to go ahead and integrate this. So you got to think, I have to increase my exponent by 1, so I get an x to the 4th, so I'd have to have a 1/4 in front to offset that. Increase my exponent by 1, so I'd have to have a 2/3 in front to offset my exponent, but I had a 3 in front, and 2/3 of 3 is a 2. Here, I'd increase my exponent by 1 to get -1. I'd have to have then a -1 with that -4 in front, so I get a +4, and then still have my plus c. Now I'll go ahead and just rewrite it with roots and moving my negative exponent back down to the bottom. Down below here, you got to think, okay, the derivative of what is a cosine, and that is a sine, and then you'd have to undo your 3 here, so you'd have to have a 1/3 in front with this, but also so it'd be a -2/3 sine of 3t. Here, derivative of what is sine, well, you know that that's cosine. You'd have to undo your chain rule of the 4 from the inside, so you'd have to have a 1/4, and it would be a negative, because the derivative of negative cosine is a positive sine, and then still remembering your plus c. So here, once again, this is in the bottom, so I'm going to bring it up as a negative exponent. And it's 20 times that. If it's a number times that, you can put that number in front. Now we just have to deal with this. So we're still going to have our 20 in front. We're going to increase our exponent by 1. So that means we'd be up to -2. Then you got to think, okay, what would I have to have in front to offset that -2? That would have to be a -1/2. But now you got to also think, what would I have to undo my chain rule? Because the derivative of the inside is a -5. To undo that, I'd have to have a -1/5. And then you still have to have your plus c. So a negative times a negative is a positive. You get 1/10 times your 20 is a 2. Still with this to the -2 and your plus c. So now all you have to do is just move that negative exponent down to the bottom. So you get 2 over 4 minus 5x all squared plus c. So now let's go ahead and take a look at your initial condition or your initial value. We know if this is our derivative, all we'd have to do is go ahead and integrate this. If we integrate that, we'd have to get an x squared. You know you'd have to have a 1/2 in front to offset that squared, which would put you with a 5/2 because there was a 5 in front. Integrate this, and then still with your plus c. Finding that initial condition basically is like, hey, find the value of c. Well, you got to think this right here means your input of x being 2 gives you out 3. So that's a point of 2 comma 3. Well, remember that your 2 is your x, your 3 is your y, so you plug that in, plug in your x being 2. Well, lo and behold, we only have one variable left, which is c, and so we should be able to solve that. And so when you solve it for c, you end up, in this case, getting c to be -3. When you're doing these types of problems, all you want to do then, once you know the value of c, is rewrite this blue line, just replacing c with what we figured it out to be. So then we get our initial condition. So in other words, this, if you do the derivative of this, we know we will get this, but we needed to make sure that this derivative, when we integrated it, went through this point. So we had to figure out, okay, how far up and down do we have to shift our graph so that we get to go through this point? And we had to shift it down 3 units. Now, you should remember from what we've dealt with before that the area underneath your velocity curve is your distance. Remember, if you're looking at area, it'd be looking at the units, this side times this side, so you get meters per second times seconds, which is meters, which is your units for area. Now, if you're dealing with velocity, we could go ahead and get velocity from looking at your distance. Remember, looking at your distance, you go change in y over change in x when you're looking at your slope, which would be meters per second. So your velocity is the derivative of your distance. The integral of your velocity is distance. Once again, opposite operations. Now, as a side note here, if we looked at our slope of our velocity, it'd be meters per second over seconds, which is meters per second squared. And so the slope of your velocity, meaning the derivative of your velocity, is acceleration. Also, since velocity is the derivative of distance, acceleration is really your second derivative of distance. If you take a look at your acceleration graph and you look at your area underneath, you would get your velocity. And once again, the units would tell you that. So that's the relationship between distance, velocity, and acceleration. With that in mind, let's take a look at this problem. We have skid marks made by an automobile that has its brakes fully applied, and it went and skidded 160 feet before it came to a stop. There was a constant deceleration of 20 feet per second squared. So that means our acceleration is -20. How fast was the car traveling when the brakes were put on? So in other words, on these types of problems, whether it's projectiles or anything like this, we always start with acceleration. Well, then we work backwards to get to your velocity and your distance. Well, to go from acceleration to velocity, we have to integrate your acceleration. So we'd have to integrate our negative 20. Well, if we integrate negative 20, we get negative 20 times t plus c. And in this case, I'm going to say c1 because we got to integrate again to get our distance. Now, in the context of this problem, our c1, because it's your constant being added to your velocity, would be your initial velocity, which is what we're really looking for because we wanted to know how fast it was going when we first started out here. So we have our velocity equation. Well, you should remember to get from velocity to distance, you have to integrate your velocity. So if I take this and plug it in here, I have to integrate my velocity. So if I integrate this, remember you'd have to increase your exponent by 1, so you get a c squared or a t squared. You'd have to have a 1/2 in front to offset that, so it gives you a negative 10 t squared, because 1/2 times negative 20 is negative 10, plus our initial velocity times your variable, plus another constant. In this case, because we're dealing with distance, this last constant would be your initial distance. Now, in the context of our problem up here, your initial distance, it would be right here at the beginning. Well, you hadn't traveled any distance at time being 0, so your initial distance in the context of this problem is 0. So we get our initial distance equation to be this. So if I bring down my velocity equation and my distance equation, I would have my distance being here, my velocity being here. So now let's go ahead and consider this. We went 160 feet for our distance. So I'm going to put 160 in. At that 160 feet is when we stopped. So that meant our velocity was 0. We now have two equations with two variables so that we can go ahead and solve this. So I'm going to go ahead and solve this for either t or c1. In this case, it's c1 is the easiest because you don't have to divide by anything. Take this c1 and plug it in right here for c1. So c1 is 20t. Plug in your 20t right here. So you'd still bring down your 160, bring it down your negative 10 squared, plug in your 20t, still with that t on the outside. So in other words, we get a 20t squared here. Well, negative 10 of the t squareds plus 20 of the t squareds is 10 of the t squareds. Now we can easily solve this by dividing by 10. Taking a square root, we get plus or minus 4. Well, it doesn't make sense to have a negative time in the context of our problem, so we know our time it takes to stop is 4 seconds. Well, once again, we were looking for initial velocity. Well, we know our initial velocity, which was c1, is just 20t. And if our time is 4 seconds, all you'd have to do is go 20 times 4, and I end up getting 80. So in the context of our problem, our initial velocity, c1, is 80 feet per second. So here we need to go ahead and figure out which one is the derivative, which one is the original. What I like to do is go ahead and start looking at this. Here, it's a max, so I know my min, or my derivative, would have a horizontal tangent. It should be 0. Well, yeah, it might be 0. But here, whoops, no, sorry. Then I look here. Well, here I'd have a horizontal tangent, so my derivative should be 0. Well, when I look here, I have a horizontal tangent, so my derivative should be 0. So in this case, the blue is the derivative of the red. So I'm going to take that approach on the next one over here, too. So I'm going to go ahead and take a look at some tangents. So here, we started out with the red over there. So if I look at the red, I'd have a horizontal tangent. Well, yeah, the derivative is 0 there. Look at the red, horizontal tangent, derivative, yeah, okay. So Looks like it could be, if I do my horizontal tangents, my derivatives would be 0. Horizontal tangent, my derivatives would be 0. Does it also work the other way around too? So if I do the derivative of this, that's 0. If I do my derivative of this, that's a horizontal tangent. So it appears to work there, but you got to also consider what's going on here. When I look here, I'm going up, so that means my derivative has to be positive. Well, it is positive here. Here, looking at the blue, I'm going down. So that means my derivative would have to be negative. Well, it is negative here. So in other words, the red is the derivative of the blue. Down below here, looking at our tangents, I could say, well, let's see, if I did a horizontal tangent here, my derivative should be 0, which the blue is not. So that doesn't work. But if I went here, horizontal tangent, my derivative should be 0, which it is. Going down to the blue here, horizontal tangent, because my slope is 0, well, my derivative is 0. So it does work there. So the red is the derivative of the blue. The last one here, I want to go ahead and take a look at, I could start taking a look at the red. Max, horizontal tangent, derivative should be 0, which it is. Look here, min, horizontal tangent, my derivative should be 0, which it is. Over here, derivative is 0, horizontal tangent, which means my derivative is 0. By the way, going in between here, I'm going up. So in between these 2 points, my derivative has to be positive, which it is. So it appears that the blue is the derivative of the red.